Okay, so we're going to prove that if the GCD of A and B is 1, then the GCD of A squared and B squared is also 1. So let's go ahead and start the proof. We're going to assume that the GCD of A and B is 1. So this implies, we know that this implies that AX plus BY is equal to 1, where X and Y are integers, right? I know I can write a linear combination of a GCD, and I know that linear combination is equal to 1. So what Burton tells us to do is he wants us to investigate the GCD of AB squared and then A squared B. So let's go ahead and do that. So we'll let D be equal to the GCD of AB squared. So this implies that D divides A and D divides B squared. And then, of course, this implies that A is equal to DK and B squared is equal to DQ, where K and Q are integers. All right, so now I'm going to go back to my equation. I know that AX plus BY is equal to 1, right? Because I know the GCD of A and B is equal to 1. So to get this B squared, I can multiply this entire equation by B. So this means I have ABX plus B squared Y is equal to B. Now, I have A, so I'll substitute that, dk, bx plus, and then B squared is dqy is equal to B. I can factor out the D from both of these, so I'll have kbx plus qy is equal to B. And what I have here is I have D times an integer is equal to B, so this means that D divides B. And I already knew that D divided A, so if I have D divides A and D divides B, this means that D divides the GCD of A and B. And from our assumption, we know that the GCD of A and B is 1, so this implies D divides 1. And of course, if D divides 1, that means D must be equal to 1. And that means the GCD of A and B squared is equal to 1. All right, so he also told us to investigate the GCD of A squared B. So I'm going to start here. So let G be equal to the GCD of A squared B. So this means that G divides A squared and G divides B. So this implies that A squared is equal to GM. I can use M. I haven't used M yet, right? GM, and B is equal to GN, where M and N are integers, right? So I'm going to go back to my equation. I know that AX, let me scoot this up a little bit. I know that AX plus BY is equal to 1. So to get that A squared, I'm going to multiply this entire equation by A. So this means that A squared X plus ABY is equal to A. So now I can do GMX plus A times GNY is equal to A. I can factor out the G, right? So G times MX plus ANY is equal to A. And of course, I have G times an integer is equal to A. So this means G divides A. And I previously had that G divided B. So I have G divides A and G divides B. That implies that G divides the GCD of A and B. And from my assumption, that means G divides 1. And if G divides 1, that means G must be equal to 1. And I set G to be equal to the GCD of A squared B. Right? Now, why did Burton want us to investigate that the GCD of A squared B is equal to 1 and the GCD of A and B squared is equal to 1? Well, he wanted us to use these two in the next piece. So now we're going to investigate. We're going to investigate the GCD of a squared b squared, which we want to show is equal to 1, right? So we have the GCD of we have f is equal to the GCD of a squared b squared. So this means that f divides a squared and f divides b squared. So this means that a squared is equal to fw. Yeah, I haven't used w yet. And b squared is equal to fz, where w and z are integers, right? Okay. So let's see what I can do. So remember, I knew that the GCD of a b squared is equal to 1. So this implies that ac plus b squared, what other variable haven't I used? E is equal to 1, where c and e are integers, right? So look what I have. I have a, but I need a squared, so I need to multiply both sides by a. So I have a squared c plus a b squared e is equal to a. And then I can substitute now, so this will be fwc plus a times, so fze is equal to a. Now I can factor out that f. So f times wc plus, let's see, aze is equal to a. I have f times an integer is equal to a. So that means f divides a. So what he wanted us to do is he wanted us to use this, right, the GCD of a and b squared equal to 1 to get to f divides a. So naturally, he wants us to use the GCD of a squared b equals 1 to get that f divides b. And then if f divides a and f divides b, that means f divides the GCD of a and b, and then we know that's 1, so that means f must be 1, and that means the GCD of a and squared and b squared must be 1. So now, yeah, how in the world would we have done that without his hint, huh? So let's see. So I know that the GCD of a, what did I do up here? Yeah, so I know the GCD of a squared b is equal to 1. So that implies that I know that a squared r plus bs must equal 1. Where, I'm gonna have to move that down. So let me move that down a little bit because I'm just out of space, or make it smaller. I'll just make it smaller. So this implies that a squared r plus bs is equal to 1, where r and s are integers. So naturally, I need that b squared, right? So if I multiply both sides by b, I would get a squared br plus b squared s is equal to b. And then from above, I know a squared is equal to fw. So fw fwbr plus, and I know b squared is fz. So fzs is equal to b. I can factor out that f. wbr plus zs equals b. I have f times an integer is equal to b, so this means f divides b. So now I have f divides a and f divides b. So this implies that f divides the GCD of a and b. So this means, of course, that f divides 1, and then this means that f must be equal to 1, which is equal to the GCD of a squared and b squared. So pretty neat proof, pretty long, but pretty neat proof. So we showed that if a and b are relatively prime, right, then their squares are also relatively prime. And that's pretty obvious, but I mean, that's an interesting thing to note. All right, and that's the proof. The proof is definitely not obvious though, right?